Hello and welcome everyone. Today we are going to look at the alternating series test, our 8th test for series convergence or divergence. We will in this video look at the theorem and its proof. As well, we'll do some examples. We'll also look at what does it mean to be conditionally convergent versus absolutely convergent. And then finally we will look at something really cool by our bud Riemann, Riemann's rearrangement theorem. All right, all of this content can be found in the textbook, section 9.5, page 631 to 636. But with that said, let's go ahead and do some math. You know what? I forgot to add one thing. There should be a bullet in between my third and fourth bullets. We're going to look at an additional theorem. It is the absolute convergence implies convergence theorem. So I'm glad I didn't forget that. I mean, we would have gotten to it eventually, but it's good to know before we get started. These are the 5 things that we're doing today. Now let's get started with some math. All right, so what is the alternating series test? What is the alternating series test? Well, here it is. Given a series from n equals 1 to infinity, of which each element in its sequence is alternating. Sign, positive, negative, positive, negative. It could look like that, or it could look like this. All right, this is just, does the first term have a negative sign, or does the second term have a negative sign? That's all I'm saying between these two. So, given an alternating series, positive, negative, if the following 2 things are true, right? If every successive term in this sequence is smaller than the previous term for n greater than or equal to 1, and I'm actually going to put a little star here, star, meaning eventually. We've seen this a lot of times. It doesn't really matter what's happening at the beginning of a series. Eventually, at some point, if this series test applies for n equals k, then you can use the alternating series test to determine convergence. Okay, so at some point, past 1, I'm using 1 because my definition here up here has 1, right, but it could be 2. And the second thing is if the limit of our sequence as n goes to infinity is 0. If these 2 things are true, then the series converges. I'm a big fan of the alternating series test. There is not much that you need to verify. You need to figure out that each successive term in the sequence is smaller than the previous term. And then keep in mind, a sub n, those are positive values. The negative 1 to the n, the negative 1 to the n plus 1, that's what's contributing the negative, positive. So we're just determining that it's almost like the absolute value, hint, hint. It's almost like the absolute value is decreasing. And if the sequence is going to 0, then the series converges. There's not a lot to check when using the alternating series test. The caveat is this only works for alternating series, which is often you're not given that. So given an alternating series, you can determine that it converges pretty simply. Before we do a formal proof, I want to do a proof by picture of sorts. And I think it's going to make this theorem make a little bit more sense for those who are still like, what the heck is going on? So I'm going to give myself a number line and place 0 right at the start of it. I want to remind myself what this theorem requires, A and B. A says that every term is smaller than the previous term in terms of its magnitude, not its SIGN, not its sign, its magnitude. And the second part says that the limit as n gets bigger and bigger, a sub n is getting closer to 0 as time goes on. So S sub 1, that's just a sub 1. So I'm going to add my first term, that's going to take me to somewhere on the number line. Right? I'm kind of here assuming that the first term is positive, which is kind of, it's without loss of generality. We can make the first term positive if we just forget about the first few terms. Once the first term is positive, we can start there. That's kind of how these series work. Right? The first several terms don't matter in the grand scheme of whether it converges or diverges. All right, so I'm going to add my first term, and that's going to take me to here, and this is actually S sub 1. Right? S sub 1 and A sub 1 are the same thing. All right, this is an alternating series. I know that the next term is smaller in magnitude than A sub 1. And I also know, and this isn't as important right now, but I know that these terms are getting closer and closer to 0, as close as I want eventually. Right, so if I add the next term, it's going to be negative, since A sub 1 was positive, and it's going to be smaller than A sub 1. So if I'm right here at S sub 1, if I add the next term, it's going to be a little bit smaller than the previous term. That gets me to right here. Right? So S sub 1 is over here, S sub 2 is over here. Remember that when I add these two things, I get my second sum. Right? Now, starting here, I'm going to add the next term. I know it's smaller than A sub 2 in magnitude. So I'm going to add some number, and it's going to fall short of where I was. This is adding A sub 3. And S sub 3 is going to be up here. Notice I'm getting closer and closer to something in the middle. Let's keep going. All right, the next term is going to be smaller than A sub 3. It's going to fall short a little bit. I'll be subtracting it because this is an alternating series. That's very crucial here. This is going to be my A sub 4. Add the next term. It's going to fall short. I'm adding A sub 5. When I add all these things up, I end up here. And so that sum is A sub 5. Let's do it one or two more times. I'm going here. I'm subtracting A sub 6. I'm going here. I'm adding A sub 7 up here. Here is S sub 6. And over here, here's S sub 7. So I'm getting closer and closer to some value. Right? Let's call that value L. I don't know what it is, but we're getting closer and closer and closer to it. All right, the last question I need to answer is the left side, my S sub 2, S sub 4, S sub 6, S sub 8, S sub 10, etc., are those going to the same value L as the right-hand side, 1, 3, 5, 7, S sub 9, S sub 11? Are these two things going towards the same value or just two values on the left-hand side and the right-hand side of L? Okay. How do we know if they're going to the same value L? How do we know that the final sum, S, is actually equal to this number in between S sub 6 and S sub 7? How do we know that? And the key is right here, the other requirement in this theorem. It must be the case that as I go out to infinity, as n goes to infinity, the size that I'm adding is eventually going to be arbitrarily small. I'm going to be arbitrarily close to L eventually on both the left-hand side and the right-hand side. And that's what a limit is. Can you be arbitrarily close to the number indefinitely? And this is my picture proof. We are alternating back and forth on both sides of a specific number until eventually we get as close as we want to that number. Let's turn this picture proof into a formal proof, and that might even more cement our understanding on the alternating series test. Let's do it. Proof. Well, let's define a few things. We want an alternating series, so let's bring that into existence. Let me get my alternatingness part of it. All right, I believe, 1 plus 1 is 2. Negative 1 to the 2 is, I want my first term to be positive without loss of generality. All right, once again, I could just cut off the first term if it was negative and start this whole proof with the second term, and it'd be positive. But that's how I want to write my, my series. Be an alternating series. Or, furthermore, let, and I'm going to write this on the next line. Furthermore, let a sub n plus 1 be less than or equal to a sub n. Right, that's kind of required. And let the limit as n goes to infinity of a sub n be 0. Right, given these two facts and the fact that we're an alternating series, we want to show that this series converges. All right. So to continue in this proof, I want to just jump back here. We're going to use this fact that we kind of generated in our picture proof. S sub 2 is less than S sub 4, which is less than S sub 6, which is less than S sub 8, S sub 10. We kind of understood that with our arrows. We're going to take advantage of that because if something's increasing, and we know it's never going to get past something, in this case L, then can't we prove that it converges? Or at least S sub 2, S sub 4, S sub 2n converges? If it's increasing, or sorry, non-decreasing and bounded, the bounded and monotonic series theorem says that it converges. I forget the name, sorry. So let's take advantage of that. S sub 2 is equal to, by definition, a sub 1 minus a sub 2. Or more specifically, it's a sub 1 plus negative 1 to the, what's it going to be? If this is 2, then it's 3, a sub 2. Right? But then it's subtraction. Just want to make that clear. We also know that this is greater than or equal to 0, since a sub 2 is less than or equal to a sub 1. That was given to us. All right, before I proceed, I just went back and I totally said 2, but I wrote an n. So let's go ahead and write 2 there. And now let's look at S sub 4. As the picture proof was trying to tell us, S sub 4 is just S sub 2 plus a sub 3 minus a sub 4. Right, the next term plus the next term. Right? In this case, once again, we're adding the fourth term. There's just a negative involved in the fourth term. Okay? Since a sub 3 minus since a sub 4 is smaller than a sub 3, this thing is positive, and a positive number plus a positive number is going to be, a number plus a positive number is going to be bigger than that number. So we have the case that S sub 4 is guaranteed to be larger than S sub 2, since a sub 3 minus a sub 4 is greater than 0. All right, what is the nth, or not the nth, because we're dealing with a multiple of 2. What does the 2nth term in the sequence of partial sums look like? Well, it's the previous term plus a sub 2n minus 1 minus a sub 2n. Okay? But we once again know that this thing is positive because successive terms, the previous term must be larger than the next term. So this thing is positive. Something larger minus something smaller equals something positive. We're adding that to the 2n minus term in the sequence of partial sums. So this is guaranteed to be larger than S sub 2n minus 2. Okay? What we've done here in general is shown that S sub 2n is increasing. Or specifically, actually, because I have all these equal signs in my inequalities, is non-decreasing. All right, I've run out of room on this page. Let's take this proof to the next one. Page number 5. Additionally, we've shown that it's non-decreasing. We need to show that it's bounded, and then we're done. We've shown, well, we're not done, but we've shown that the S sub 2, S sub 4, S sub 6, S sub 8, that is bounded. We'll show that that converges. Then we need to deal with the other side. Well, let's jump back to that page, this picture proof. And I think that it's kind of obvious. I don't want to be, I don't want to jump to conclusions, but I think it's obvious that S sub 2, S sub 4, S sub 6, this is always less than S sub 1, all right, which is equal to, S sub 1 is equal to A sub 1. I believe that S sub 2n, Let me go back here. Idea. S sub 2n is always less than or equal to a sub 1. If we can show that this is true, then we've shown that this thing is bounded. Right? If we've shown that it's bounded, we just show that it's not decreasing. We can show that this thing converges if we can get that fact right there. Well, what is S sub 2n? Written out, right? Well, it's a sub 1 minus a sub 2 plus a sub 3 minus a sub 4 plus a sub 5. I'm going to write plus, or I probably shouldn't. Let me go ahead and do this. Plus dot 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 all the way down to plus a sub 2n minus 1 plus a sub 2n. That is what S sub 2n is. It's the 2nth partial sum. Right? I can rearrange this, though. Not rearrange, but I can rewrite this. Watch this. A sub 1 minus a sub 2 minus a sub 3 minus a sub 4 minus a sub 5. Notice that I have still a positive 3. And I still have a, well, I would have had a positive 5 if I had written that. Right? And I'm going to write another minus dot 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 a sub 2n minus 2 minus a sub 2n minus 1. I got my positive 2n minus 1 minus, plus a sub 2n. Oh, nope, I meant minus. And sorry for the people that are freaking out up here. I also meant minus up here. It's alternating. Take a second to think about why I have shown that a sub 2n is bounded above by a sub 1. What is the sign of this thing? A sub 2 minus a sub 3. We have the fact, but a sub n plus 1 is smaller than a sub n. So this thing must be positive. This thing, something bigger minus something smaller, must be positive. We are subtracting positive values from a sub 1 every single time. And then this thing is positive. We're subtracting a positive thing. That's the way we constructed this alternating series. So S sub 2n is bounded above by a sub 1. Since S sub 2n is bounded above and non-decreasing, S sub 2n converges. Actually, let me write this. The limit as n goes to infinity of S sub, not n, 2n converges to some value L. All right, we're not done. We've shown that S sub 2n converges. We have not shown that S sub n converges. Our goal is to show S sub n converges, not S sub 2n. So what do we do? Well, we've dealt with the left-hand side. We've dealt with the S sub 2n's. What does that equal? Well, we can look at the right-hand side of my little picture proof. Well, look, this is what I want, 2n minus 1, right? Well, how are these things related? These are not equal currently. Right, but, let me add a little but. These are equal. Let me finish writing. Those things are equal, right? Why are these things equal? Well, because S sub 2n is equal to S sub 2n minus 1 plus the next term, A sub 2n. Of course, you can just take the limit of both sides, and the limit laws apply to addition. So this is true. Well, What was our other initial condition? Right, right here. The limit as n goes to infinity of a sub n is 0. Right? If it wasn't 0, we might not be able to do what I'm about to do. Sorry, I'm taking a little bit of time to get back here. We're back here. This thing right here, or sorry, not that thing, but this thing over here, that goes to 0. Oh wait, so this is true up here. I'm a little question mark because down here, we are given in our initial proof, or in our initial conditions, that a sub 2n goes to 0. So, since this is 0, the limit as n goes to infinity of s sub 2n is equal to the limit as n goes to infinity of s sub 2n minus 1. This is telling me that, let me go back to my picture. Both sides, the even side and the odd side, are both approaching the same value L. These are both approaching the same value L. Thus, S sub n, the even and the odd sides, are both approaching L. Let me add my limit symbols. Regardless of if I'm dealing with an odd or an even element in my sequence of partial sums, both subsequences are approaching the same value. We have a convergent series. Thus, the limit as the sequence of partial sums goes to a value, and the sum of -1 to the n plus 1 times a sub n converges. We have proven the alternating series test. B, G, T, D. Boom goes the dynamite. Once again, the alternating series test tells us that if we have an alternating series, and since every next term is smaller than the previous term, and the sequence that we're dealing with, its limit is 0. That's the key. The limit is 0. Then both the left-hand side and the right-hand side are going to the same value. Alternating series converge if these two conditions are met. Let's use it. All right, using the alternating series test. I'm going to abbreviate it with AST. All right, example number 1. Let me just write example 1. Using the alternating series test is pretty straightforward. Here is my example. It's, of course, an alternating series. 1 over the square root of n. Right? Think about this without the -1 to the n. 1 over the square root of n. Right? P-series test tells us that this thing is going to diverge. However, because it's an alternating series test, because it's an alternating series, maybe the alternating series test is going to tell us that this series converges, as opposed to its absolute value. Right? So let's look at the. So let me just make something clear. A sub n here is equal to 1 over the square root of n. So criteria 1, let me use 1 instead of a. Criteria 1, what's the limit as n goes to infinity of that thing? Well, that's 0. Right? So criteria number 1 met. Sweet. Criteria number 2. Is every successive term less than the previous term? Well, what's the nth plus 1 term? That's 1 over the square root of n plus 1. And that is certainly less than or equal to the next term, or the previous term, sorry. Right? Previous terms are larger than the next term. Right? This is true for all n. True for all n. Boom. So I guess a good person would write it at the bottom and write down top to bottom, but I'm going to use the space that I have up here, this empty space, by the alternating series test. Since a sub n, the limit of a sub n as n goes to infinity, is equal to 0, and a sub n plus 1 is less than or equal to a sub n, the series converges. Awesome. Another quick example. Example number 2. How about negative 1 to the n times 1 over n squared? Now, the limit of 1 over n squared as n goes to infinity is 0. Check. 1 over n plus 1 quantity squared is less than or equal to 1 over n squared. Check. Right? The limit as a sub n as n goes to infinity was 0. A sub n plus 1 is less than or equal to a sub n. By the alternating series test, this series converges. Very easy test to use, but it only works for alternating series. All right, notice that my a sub n here converges. 1 over n squared, we know that by the p-series test, that thing converges. My previous example, 1 over the square root of n, that thing diverges. We know it through the p-series test. Right. So the alternating series test only tells us if the alternating series converges. It doesn't necessarily tell us that the actual series, or the series without the negative 1 to the n converges. So be very careful. This only works. This beautiful, very easy to use test only works for alternating series. With that said, I have some vocabulary for you. Conditionally convergent. Put an R right there. Conditionally convergent versus absolutely convergent. A series is conditionally convergent if a sub n converges, but a sub n, the absolute value of then diverges. Right? And a series is absolutely convergent. Let me go ahead and get rid of this versus. If the series itself converges and the absolute value also converges. We call a series conditionally convergent if it converges but its absolute value doesn't. And we call a series absolutely convergent if it converges and its absolute value also does. Let's go back real quick. My first example. This is, let me write a different color, conditionally convergent. Right? Because the series itself, it converges. But its absolute value diverges. All right, that's a p-series test problem. Feel free to do it if you want. All right, my second example. This is absolutely convergent. Because the series itself converges. And without the negative 1 to the n, the absolute value of this series, 1 over n squared, also converges. Why am I saying this? Enter our final theorem of the video. And this one's pretty powerful. Right? This is the absolute convergence implies convergence theorem. If the absolute value of a series converges, then the series itself converges. Let me go back a few pages, as I've been doing, and kind of talk about this example right here. If you can show that 1 over n squared converges, then you don't even need to use the alternating series test to show that negative 1 to the n times 1 over n squared converges. If the absolute value converges, then regardless of if there's negative values in the series, it must also converge. This is great for series that are not really alternating, but do have negative and positive values. If you can show that the absolute value, if the positive version of all the terms converges, then the alternating bits must also converge. The textbook has some great examples of why this is useful. One of them is, does this thing converge? Like, this is not a true alternating series because sine 1, sine 2, sine 3, sine 4, sine 5, that may or may not be alternating. It also contributes a ratio. Sine is between negative 1 and 1, so our numbers are going to either be 1 over n squared or smaller than 1 over n squared. Right? But what this theorem says is if you can show if the absolute value converges, then the original series must also converge. And I think that you guys absolutely have in your wheelhouse the ability to show that that converges. Right? Some other examples, or at least one more example. The textbook gives you this ridiculous thing. The sum of negative 1 to the n times n plus 1 all divided by 2 all over 3 to the n. Right? Does this thing converge? Well, looking at this numerator is an eyesore. But if the absolute value of this thing converges, and the absolute value of the numerator is just 1, if the absolute value of this previous series converges, then the original one must converge. So this is the power of this new theorem. Absolute convergence implies convergence theorem. All right, let's prove this thing. I'm making a lot of bold claims about these ridiculous series and how they converge just because the absolute values converge. So let's confirm that this is actually facts. All right, proof. What do we know? Right. We know given the series a sub n's absolute value converges. This is our assumption. With that said, I'm going to write something down, and I want you to take a second to think about why it must be true. Why must this statement be true? The opposite of a sub n must be less than or equal to the absolute value of a sub n. All right, this must be true because either they're the same thing and they're equal, or negative a sub n is negative and they're certainly less than the absolute value of a sub n. This is a certainly true statement. Right, what I'm going to do is I'm going to add a sub n to both sides. Boom. Right. You can also think about why this must be a true statement as well. Right. A sub n is guaranteed, or absolute value of a sub n is guaranteed to be larger than whatever this number is, whether or not it's negative. They're absolute values. So this is going to get us into the positive. Or it's going to be equal to 0 if they're opposites. Similarly, a sub n must be less than or equal to the absolute value of a sub n. Right? This is a very similar statement to over here. A sub n must be less than or equal to the absolute value of a sub n. Right? Either they're the same thing or a sub n is negative. Right? If I add the absolute value of a sub n to both of these, I'm going to get a sub n plus the absolute value of a sub n is less than or equal to 2 times the absolute value of a sub n. So these two statements combined give me that Let me get my equal signs in there too. I have these bounds on a sub n plus the absolute value of a sub n. It is certainly positive, and it's certainly less than 2 times the absolute value of a sub n. So my question to you is, can we determine, not a sub n yet, but can we determine that a sub n plus the absolute value of a sub n, the series, converges using this statement here? And the answer is, yeah, by the BCT, must converge, right? This thing, because converges. And the sequence is both positive and less than this sequence. And this is the basic comparison test. It is less than and positive, and because the larger one converges, the smaller one must also converge. So what have we shown? We've shown that the sum of a sub n, plus the absolute value of a sub n converges. We're not done yet. So far, we have shown that this converges. All right, what does this converge to? I'm not sure, but I do know that it converges to something. Oops. Let's get that there. This converges to, let's go ahead and say L. Right? But let's use summation rules. Right? I can split this thing up. A sub n plus the sum of the absolute value of a sub n. That is equal to L. Right? And our initial assumption says that this converges, and it converges to something. Let's say it converges to M. I don't know. If this converges to M, a sub n plus M equals L, and then we have shown that a sub n converges to something. Q, E, D. Actually, before I write this Q, E, D, let me make my final statement. Therefore, if the absolute value of an converges, then the sequence itself, or sorry, the series itself must also converge. There it is. Once again, this will be useful when we're dealing with things like these two things. They're not true alternating series, right? It kind of just depends on what sine of n is, and it depends on what this thing is. These are not truly alternating series, but we can utilize their absolute value to determine that they also must absolutely converge. We'll give you some examples in class to exercise this theorem. With that said, I got one last thing to do with you guys before I close this video out. We've been giving absolutely convergent series a lot of accolades. Let's give some conditionally convergent series some accolades. So there's something really cool that you could do with conditionally convergent series. So it is called Riemanns Rearrangement Theorem. We're not going to prove this one as formally, but here it is. If a series, this is just mainly for the enjoyment of mathematics. If a series is conditionally convergent, for every real number L, there is an arrangement of the terms in the series such that the series converges to L. What does that mean? So if a series converges but its absolute value doesn't, then you can take the numbers in that series, the sum, and rearrange them so they add up to whatever you want? Huh? And this doesn't work for absolutely convergent series? I think a picture will help. Let's say I have the series -1 to the n times 1 over n. This thing is conditionally convergent. All right, why is it conditionally convergent? Well, real quick, by the AST. This, I believe, converges because the limit as n goes to infinity of 1 over n is 0. Check. And 1 over n plus 1 is, in fact, less than or equal to 1 over n. Right? So this is a convergent series. Right? But the absolute value of it, so which is that just going to be 1 over n? Right? Diverges. It's the harmonic series. Diverges by the p series or harmonic series. The harmonic series. What are the terms in this series? So our first term, let's go ahead and say n is equal to 0, just for the sake of the first term being positive. Once again, it doesn't matter what the first terms are. All of these tests are about eventually, because we can separate the first set and then the rest. And then that first set is just a number. Right? Any finite series equals a number. But anyways, we have 0. That's going to be, 0 is not a good term. My bad. Let's go ahead and make it 2. Just so that we have 1 over 2. Then we have minus 1 over 3, plus 1 over 4, minus 1 over 5, plus 1 over 6, minus 1 over 7, plus dot, dot, dot. Okay. This series is conditionally convergent. Riemann's rearrangement theorem says that I can make these numbers down here add up to whatever I want. Well, the sum of these things, or the absolute value of the sum of these things, will never, there's no bound to that. It can get as big as I want. But I have these negatives. But if I have 1/2, 1/4, 1/6, 1/8, that can get as big as I want because it diverges. And similarly, -1/3, -1/5, -1/7, that can get as negative as I want. It can get as big as I want because it is also divergent. Right? The convergence of this depends on the positive and the negatives working together to kind of alternate towards something in the middle. This can add up to whatever I want. Let's say I wanted to add up to my favorite number, 47. Here's a number line. Let me go ahead and move this up so I have a little bit more room. Let's say I have a number line. Let's say I wanted to add up to 47. All I got to do is pick enough positive numbers so that I get past 47. Then start picking negative numbers so I get on the left side of 47. And the key here is that I can get to any number because there's an infinite amount of terms in this series. Then I just need to pick some numbers until I get past 47. Then start picking some negative numbers until I get past -47. Then start picking some numbers and just boom, boom, boom. And then I can converge on my favorite number, 47. This sums to 47. Here's the issue with this. This is what Riemann's rearrangement theorem says. Same series. 1/2 minus 1/3 plus 1/4 minus 1/5 plus 1/6. I'm going to write the same amount as I did before. Plus dot, dot, dot. Let's say you're a Hitchhiker's Guide to the Galaxy fan and you want to add up to the number 42. Just pick enough terms in this series until you get past 42. Then pick enough of the negative terms so you get on the left side of 42 and the right, and you can just keep doing this until you converge on maybe your favorite number, 42. If a series is conditionally convergent, there are enough positive terms and enough negative terms in the series to get past and then to alternate back and forth between whatever number you want. Riemann's rearrangement theorem says that a conditionally convergent series converges to whatever number you want. This does not work for an absolutely convergent series because the series itself, the absolute value, converges to something. So there's not going to be the terms in the series that it's necessary to get to maybe 42. Maybe that series converges to 2 and you can't actually get past 2. An absolutely convergent series converge to something specific. But conditionally convergent series converge to whatever you want. And that is one of the many things that is beautiful about math. And that's what we're going to finish this video with, Riemann's rearrangement theorem. Wow. It's called the rearrangement theorem because all you got to do is rearrange these numbers so that you have enough positive ones first to get past the number that you want to converge to, and then you can have enough negative numbers next to get less than the number you want to converge to. And by the way, this also works for negative numbers. You just flip the signs. And then you can put some more positive numbers to get past it, some more negative numbers to get past it, and then just keep doing this until you converge on that number that you want. 42 maybe for you. Maybe you have a different number that you like. 47 for me. Let's take it back to the beginning. Let's review what we did today, and then let's get out of here. The power of pausing. Here is the first slide. We looked at the alternating series test and its majesty and its power and its beauty. It's a really great test, but it only works for alternating series, which is kind of unfortunate. But you only need to check two things. Are the terms decreasing, and are they moving towards 0? Right, we did some examples. We didn't do a ton of examples, but I think it's going to be okay. We're going to get some examples in class. And then we looked at conditionally versus absolutely convergent theorems, convergent series, and we got two theorems. If the series is absolutely convergent, then, if the series is absolutely convergent, meaning that its absolute value converges, then the series itself must also converge. This is useful for when it's not a true alternating series. And also, we looked at Riemann's rearrangement theorem, one of the beautiful things of math, that if you have a conditionally convergent series, it can add up to whatever you want. Right? Once again, all of these things are covered in 9.5, so take a look at it, read through it. I find that reading through the textbook before and after a lesson is super useful, so take advantage of that now, next year in college as you move forward. Textbooks are very useful, and it's good to become one of their friends. All right, with that said, I'm going to close this thing out. Have a great Thanksgiving break, and we will see you next week.